Go ahead and
Okay, John's on it. All right. Hi, everyone. My name is Josh Persi. Today we are discussing Chapter 10, Function Factories of the Advanced R book, written by Hadley Wickham. It's exciting, Function Factories. Full disclosure, it was Canadian Thanksgiving this weekend, so I am not like prepared to the gills. I think I'm prepared enough to lead the presentation, but if you have insights, you would be doing me a favor if you shared them. So be liberal with your interjections. Okay, function factories. First slide. By the end of today's session, I hope that you will be able to identify function factories when you see them in R code out in the wild, understand how function factories work and what features of R kind of allow them to work, to learn about some non-obvious combinations, basically use cases of different function features and function factories in general, and how using functionals and kind of like the idea of iteration, you can create a whole slew of different functions from data you input into it. Okay. So what is a function factory? Just like a real life factory, it produces things. In this case, it produces other functions. So a function factory is itself a function that returns a function. One thing I think of when I read these is this power1 function factory up here is a classic function in the sense that it is defined with the function argument. And its body is really small, but the last thing it's returning, or the last thing within the body, the thing which it is implicitly returning, is itself a function. So I think out in the wilds, if you're reading the rather long body of a function, if it returns a function, either explicitly with the return function, or if it implicitly is returning a function by having the function be the last thing in the body, you're kind of dealing with a function factory by definition. Is at least my understanding. So this function factory, power1, so-called because there is already a power function, but so the one doesn't really mean anything here. But we're taking one parameter, the exponent parameter, and we're returning from power1 another function that is nameless in this case, that has one parameter x, and the function will return x to the power of whatever the exponent is. So this function factory can be used to create other functions called manufactured functions. Manufactured functions are functions produced by a function factory. So in this case, we can use the function factory, power1, with 2 as the argument for the exponent parameter, and we get a new function called square. And square can be used just like any other function. You write square into the command line or into your script with the x parameter here being 2, and 2 to the power of 2 is 4. Same idea, cube is another manufactured function created by calling the function factory with a parameter here with an argument for the parameter of exponent. And we create a new cube function. 2 to the third power, 2 cubed is 8. So that's just maybe a bit of what a function factory is. Hopefully you'll be able to identify one if you see it out in the wild. Something that produces another function. Just gonna grab a sip of water. R has a couple features, as we've been learning throughout this book, that give rise to function factories. I'm not sure how unique, I guess, function factories are to R, like, or if other languages without these particular aspects of R implement function factories in a different way. I'd be interested if anyone knows more on that. But three things about R that give rise to function factories, at least as they are implemented in R, is one, first-class functions. By this, I mean that, or it is meant that functions are first-class objects, just like any other object. You can name them, you can bind them to environments. You can, I guess, inspect them. I'm not entirely sure what it all the term first-class functions encompasses, but here I think the important thing is that we can like easily create them. Like there's nothing, I guess, there's no particular syntax. Well, like there kind of is, but
I think it's basically that they can be arguments and they can be returned from functions. Like they are data that
yeah,
it can be attached to names. They can, you can do all the things that you can do with any other data.
mhm. That's a good point. And I think if we go back to this, where we're like normally in a function, you would return an object of some sort, like an integer, a data frame, something. Here we're returning a function just as if it was like any other object, because it is, I guess, like any other object. Our functions also capture the environment in which they are created. They enclose the environment in which they are created. And this means that manufactured functions capture the environment or enclose the environment of the function factory. So every time you create a new manufactured function, you're enclosing the environment of the function factory. And our functions also create a ephemeral, short-lived, temporary execution environment by default. This is the fresh start principle we learned about in a previous chapter. And if you recall the two manufactured functions we created, square and cube, these both have their own function environments, as shown by the memory addresses here being different. But they both enclose the function factory environment, and the parent of that is the global. I still struggle to, my like mental model of all of it is still not great, but this property of enclosing the function factory environment is why in both of these functions, square and cube, you have the exponent object that is defined in the function factory environment, in the enclosing environment. Just going to take a pause to see if anyone has chat messages that I need to address. Okay, an observation about object size, but I'll just leave that be for now. A diagram of how function factories, manufactured functions work in the context of like environments and enclosing. This is maybe the more complicated version of the one shown in the book. I like to try to wrestle through it. Maybe folks can correct me if I say something incorrect. But here we have our global environment in the gray, and we have our functions that we've defined, square, cube, and power1 that live in the global environment. Power1, the name power1 is associated with this function. That's what the like yellow rounded rectangles are, their functions. So this is a function, x is a function, or the cube here is a function, and the square. The thing associated with the square name is a function itself. The one argument of the power function is, or the one parameter is exp exponent, and the enclosing environment shown by the black dot here of the power1 function is the global environment. We also have connections between the power1 function which is the function factory, and the manufactured functions by way of the enclosed environments that they've created. So these manufactured functions, square up here and cube right here, these are both functions, the same kind of function in a sense. They both have their own versions of separate environments that enclose the function environment. That's what these blue dots, the dots here are environments, and the blue dot is a parent. So the parent of the square environment is the power environment, power one environment, and the parent of the cube environment is the power one environment. And because they've enclosed, we see the exp argument is available in their enclosed environments. Hopefully I didn't say anything too wrong there. Hopefully that was insightful as opposed to annoying, but we'll keep going from there. The maybe this is one area where I still struggle, is like the difference between a enclosing environment and an execution environment and a function environment. But this is, I think, the last diagram I have here, so we'll quickly walk through it. This is taking the one manufactured function, square, and this is the function right here. The execution environment is up here in this gray box. So the execution environment is where X is defined, or at least it's available. X in this case is 10. This execution environment, which is temporary, it'll be deleted after the execution finishes. It is a child of the function environment and of square, and the function environment of square is itself a child of the enclosed environment that was enclosed, captured at the time the manufactured function square was created. So I'm also the one who gave the presentation on the environments chapter, so I was, I guess, particularly interested in this. And there's just a lot going on, even for like a relatively simple thing like this, that with respect to environments, that I think is a little interesting. Okay, for manufactured functions, they are lazily evaluated, or rather objects within them are lazily evaluated by default. Lazy evaluation is something we've talked about already. It's a feature in many places of R, but in this context, what it means is maybe best illustrated through an example. Let's take the code chunk over here on the left, where we are defining X as a name is associated with, where the value of 2 is bound to the name of X, to the letter X. And we are using the function factory, power1, to create a manufactured function called square, with X being the exponent parameter. We then rebind or change the binding of X to be 3. Now, when we actually call the manufactured function, X is being evaluated, or square is working as if X is equal to 3. You take the base 2 and you are putting it to the third power. That's equals to 8, and that's what you see we get down here. Even though when we define square as a manufactured function, X was 2, because of lazy evaluation, the X actually wasn't evaluated because it wasn't needed until we called the square function itself. And by the time we called the square function, X had a new value. This can create some annoying bugs. In general, I think the word of warning is to be cautious about changing the bindings of objects or variables between creating the manufactured function and actually executing it. But if you need to get around this, you can use the force function shown here on line 2 to make the exponent argument be eagerly evaluated. And as you can see, if we use the updated power2 function, which has a force call to eagerly evaluate the exponent, regardless of what we set 3 to after the fact of declaring square, we get the expected, I guess, output in this case, where the square function is truly putting the base to a squared exponent to the power of 2. You don't need to use force per se. You can use any other function that evaluates your argument, I believe. So you could, if it made sense within the function you were writing, you could write like print the length of your argument, which would evaluate your object and kind of have the same output as force, or same effect as using force, but it might also produce output you're interested in, depending on the function you've written.
And I would point out that I would always, well, except for in the weird cases that we're going to see in a minute, but I would always force in a function factory, even if you don't know that you need it, like just to be safe. And
Just as a good
another
habit.
thing, yeah. And I love force because, like, if you look at the definition, that is what force is it's just return its input, but because it does that, it evaluates it. So
Okay, interesting.
You could also say like print exp. I think that would do the same thing, but force, lets people know why you're doing it. Basically.
Yeah. For the goal of forcing evaluation as opposed to printing output. Okay, good. And force is new to me. What is the convention? And I haven't really inspected too many other R functions that use it, but just throw it at the very top along with any stop if not or assertions.
Yeah.
Okay.
And that's the other side of it. If you assert, then you're effectively forcing. So it's just if you're not doing anything else to validate the input.
Okay.
Force is it's kind of a baseline.
Gotcha.
Validation.
Okay, thank you. Just gonna pop into the chat for a second. Feel free to, I'm not seeing any questions for me in the chat, but if you have questions, you're more than welcome to hop on the mic and ask them. Another thing you can do with manufactured functions, because they uniquely capture their enclosing environment in a distinct and unique instance, a new environment. You can have separate, every instantiation of a new manufactured function has its own environment. And because of that, you can do things like this example where you have, I'll walk through it here. You're creating a new counter function. Your new counter is your function factory. You're setting I to 0. And the manufactured function you're going to produce will increment I using the super assignment operator, the double chevron hyphen, by 1. It'll increment it by 1 and then return the incremented output. You can create 2 new manufactured functions, counter 1, counter 2, from the function factory new counter. And every time you call the function, manufactured function you're incrementing. But as you can see, no matter how many times we increment or we call counter 1, counter 2 is unaffected because they have separate my understanding is they like both enclose the function factory environment, the parent environment, but they create like different instances of it. So you're not going to contaminate one manufactured function's enclosed environment by meddling with another manufactured function's enclosed environment. So you can do things like this. But the book cautions that if you're going to be messing around with state a whole bunch, you might want to use an object-oriented system like R6, which is a upcoming chapter, I think, in a few chapters. So stay tuned for that if state is something that interests you. One thing that one thing about the super assignment operator, I feel like I still don't have a great handle on it. So I maybe want to make a statement and people can correct me if I'm wrong. I think it comes down to something earlier in the book. There was like emphasis put on the distinction between modification, if it exists, and creation, if it doesn't. My understanding is that super assignment will imagine you're like in a heavily nested environment kind of hole. And if you use the super assignment from like the child environment, it will look for for that object in a parent environment, modifying it if it exists. But if it never finds it in any parent environment, it will create it in global. So it won't create the object in the parent environment per se, unless your parent environment is also the global environment. Not sure if anyone has strong opinions or wants to correct me if I'm mistaken. I see some chats. Okay. Anyone? Did I say something wrong? Does anyone have any strong opinions? Feel like they really know what the super assignment operator does?
Right. My understanding of that documentation states that the super assignment will go back through the list of environments until it finds, in this case, until it finds the variable I. So since variable I was just defined, initiated with 0 in the new counter execution environment, then it's gonna stop there. But if it doesn't find it, it'll go up the list, maybe all the way to the global environment, and it will create I in the global environment, which I think is shown in the next example, in that chapter. Yeah. So
Okay.
I've been trying to do something like that with the sign, and I ran out of ideas because I wanted to return something. I needed to create a name with some paste or glue or whatnot, and assign something to that name, and just map over the list of names to put into the parent environment. And I just gave up and written those. I needed to return like 4 or 5. I thought it would be more elegant to do it with a map over a list, but since I failed to do proper assign, I just did it with 5 lines of this.
Gotcha. Okay.
Super assignment. Okay. So that's what my question in the chat is about. If there is what is an elegant way of using a sign inside that factoried function in that code, if there is a way to do that with a sign.
I'm not sure I fully understand the issue. In case it, like, I think I do conceptually, but this might not be exactly what you're looking for. But I've done like iteration with assignments using like per walk for, I guess, like the side effect of assignment. I'm not sure if that's a great use case or if it is relevant to what you're looking to do, but I feel like I've done something similar with like creating a name with glue or paste. assigning, like passing that as a argument to like per walk2 along with a list of objects I want assigned, and then using the assign function and specifying the actual environment parameter to whatever environment I want to create the objects in. I feel like that's worked for me satisfactorily, but I'm not sure if it's exactly the use case you have in mind.
Yeah, more or less, yeah. I mean, creating stuff in the current environment with the sign is, well, just as it is, but just figuring out this whatever needs to go inside the environment parameter of a sign. That's where I got stuck.
Gotcha. Okay. Martin?
Yeah, I think I have a question about the role of the super segment in this function. I mean, the role is that we are replacing the I being 0 from the parent environment and like replacing it with I plus 1. That is the purpose of that here.
Yeah, that's my understanding. Except when you call the function, like the actual manufacturer function, you're just calling this bit. So I won't actually be 0. It'll be whatever it returned on the previous execution of that function.
Okay.
This bit is just to set like the starting point for the counter when you make your new manufactured function, as far as I understand.
Yeah, I think I'm getting it. Thank you.
Awesome. Okay. We can keep rocking and rolling.
Kind of retained statement on something like retaining the initial value. Is that true?
Sorry, could you repeat that for me?
No, that's kind of having a retain value. The retain initial value is, or a seed value is 0, and then add it up to that.
Yes. Yeah, I believe so.
Thank you.
Okay. We've kind of gone through some like quirks, I guess, of function factories. Maybe another quirk is garbage collection is something you might actually need to pay attention to, whereas most of the time you don't. This is because each instantiation, each new manufactured function you create captures your function factory's environment. So if you have large objects in your function factory, those are getting kind of duplicated, as far as I understand, every time you create a manufactured function. That's by default. So you can see that over here. We have a function factory called F1, which is taking an integer called n, and we are creating a uniform distribution, a bunch of other numbers. I believe the size of the integer that you specify. And then we're taking the mean of that distribution, and we're returning that mean as like the output of this function. So when you actually call F1 with the number here, 1,000,000, and create a new manufactured function called G1, the object size is quite large because it's enclosing x, which is a numeric vector of length 1,000,000, which is fairly large, I guess. And because there's no garbage collection here, that's getting passed on to your manufactured function G1. And you can see the size of G1 is 8 megabytes. And if you were to like create G2, G3, G4, G5, you would be recreating. You'd also be storing the large integers or large vectors within each of those functions. So what you do here is you just remove the object since you don't need it anymore. In this function, you've already used the large vector of numbers to calculate the mean, which is like a vector of length 1, scalar, or atomic, if I'm using those terms correctly. You remove the big vector and you just return the atomic value, like the atomic object, the one value. And you can see that the object size is much smaller because of that. So something to keep an eye out for if you're making a lot of manufactured functions. The book has a lot of different examples, which I haven't included here. Not all of them, I guess, are like immediately. I don't really have much to say about any of them, and I don't know if pulling them into slides would really be something I could speak to, but we can go to the book if there's interest in discussing the chapters or the examples. I would be keen to get a sense of how everyone else uses function factories after maybe this last slide that comes at the end of the chapter on combining functionals like per map to handle iteration across like a list of data objects, and combining functionals with function factories to make unique manufactured functions given your like input list of data. So in this example, we're still like doing mathematical transformations, taking things and putting them to an exponent. We have a bunch of different, we're creating a list of a bunch of different named values. So square gets the name of, or the name square is associated with 2, the name cube is associated with 3. These are all different exponents that we want to create functions with. So we could have a square function, a cube function, a root function, a cube root function, and do all these mathematical operations. Using per map, which we talked about in functionals, the previous chapter, we take your list here of names and you apply the power1 function factory to create a bunch of different functions. So if you were to inspect functions here, it would be a list of functions, which you can access individual functions from using the $sign operator. So functions root with the base, or I guess the value of 64, and the square root of 64 is 8. And you can inspect the body of the function, the root function, with the $sign operator as a prefix. You can do some things to pull those functions out of the list from wherein they reside, and make them kind of like normal R functions. You can use with the functions list, the function name, and then the argument. You can attach the list of functions, and these make them, I guess, accessible on your search path. They will mask other things just defined in your global environment. The last method that's talked about is using rlang to and the triple bang operator, which we will learn about, I believe, in a subsequent chapter, to bind the functions within the funds list to the global environment, and then you can call them just with no prefix, no $sign prefix. Those are all the slides I have. I'd be keen to know how others are using function factories. Maybe before I pass it off to anyone else who wants to share, the book mentions that function factories are like relatively unused compared to functionals like iteration, which is used all the time, and function operators. And my sense is that functional or function factories are more of like you can avoid function factories and program the same end goal with other techniques. It's just if you or your team really like function factories and you think they are like a good thing, like they can, and you all like kind of agree to use them in certain circumstances, they can be like an elegant solution, a shorthand to do things, but potentially a very powerful shorthand, but like you could do other techniques and get the same result, I think, if you like have a strong aversion to them. So that's, I think, everything I had. We can turn it to the group if you have ideas, questions, input, or we can go through some examples from the book. So yeah, and presentation, I guess.
So technically, if you work in Shiny, reactives are the Shiny reactive function is a function factory. It is creating functions that have a special class. And then he has the scales example. Those are the two big ones.
With Shiny reactive, is it a function factory because every time you like call your Shiny app, like I guess why are they function
Yes,
factories?
because the server function, well, so there are function factories all over Shiny, really, because if you work with modules, you're creating functions that your server will call.
Yeah. Mm-hmm.
And so it's that when like a new instance of the Shiny app is launched, it creates that reactive, which then is a function, so that, you know, that's how you call the values of a reactive.
Okay.
And because you need it to be a function because you're getting like the live value. And so that's why.
Okay. I think that's the bit I was hung up on, but okay, yeah.
Yeah, there's a combination of R6 and function factories in Shiny is where all the magic comes from, basically.
Okay.
That's the only place I can think of where I like actively use them, but day to day I'm programming in Shiny all the time right now, so I use them a lot because Shiny. Yeah, and that's when you get into really weird things because, you know, if you have ever seen the famous error message object of type closure is not subsettable. Well, a base function isn't subsettable, but you can give a function a class and then define what happens for that class, for $ with that class, and make it subsettable. So, or for bracket with that class. Yeah, technically, in a lot of modeling, you're creating functions, really. And so like any function you call to build a model is a function factory.
Yeah.
Probably. Yeah. So
maybe this is like just a question for you, John. I don't know anything about the R6 object-oriented system or like object-oriented programming really in general, but are function factories something that like work hand in glove with an object-oriented system, or is this something that is like really just a functional programming language thing?
looking at them this way is functional thing,
Okay.
but when we look at R6, like you're creating objects that have methods, and methods are functions. So when you create a new instance of that object, you're basically calling a whole bunch of function factories to create that thing. Kind of. Most like the methods tend to be not very factory. It's a little different. It's more that they're like attaching methods or attaching functions that have a shared environment. So not quite exactly the same as a function factory, but pretty
Okay.
close.
Okay.
Yeah, I think they probably come up more than I can think of, and you just like don't notice. Like the scales stuff, it doesn't
Mhm.
feel like a function factory until you start working or thinking about it. And you're like, oh yeah, you create
Yeah.
a thing that you call, or that is being called by ggplot, basically.
Mhm.
And there's probably a lot of function factories in ggplot, actually. I'm not sure. But yeah, it's neat to know. I love things like the iterators that are just like, wait, what? That, oh, okay, that makes sense, I guess. But that will make more sense with specifically with R6. R6 is basically a wrapper around environments. It is, hey, environments are kind of cool. What can we do if we have just encapsulated environments that we're passing around? Oh, that's object-oriented programming. Okay. So, yeah.
I saw
I
a
definitely
couple other
think,
hands kind of come
yeah.
up and go down. If anyone, you're welcome to bring up your comments or questions or feedback.
Yeah, for sure.
I think I just wanted to say that example in the book, like the exponentiation example, is like the best example that I can think, like in what I'm doing on daily basis, like analyzing data. But I cannot think in another example, like a simple example. Maybe with ggplot or maybe with Shiny. Like if you dig enough, you will get that maybe some things are function factories, but I think like on like a simpler example is the exponentiation example. Yeah, that's it.
It's really hard to search for too. Like I was trying to think, how could we find some examples? Like, are there other examples in the tidyverse? Searching for function, like, yeah, there's function all over the place. I guess maybe
Yeah.
searching for force could
Yeah, that could be
find
good.
some interesting, except that won't actually work because as we'll see when we get to like the metaprogramming chapters, they don't build function factories the base R way.
Anymore.
They
Okay.
yeah, they build them with rlang where you are like creating the function with, well, actually they do both. But yeah, that was I posted that I have the package factory that I have almost never used. But it was a fun programming exercise. It makes it easy to create a function factory using the rlang stuff. So the only difference being when you print a like square, it doesn't make sense. Like it shows the the raw version of the function with exp, and it doesn't tell you what exp is, and so you can have things that happen that are weird. Versus if you use the rlang stuff, you can make it like the definition of the function shows the substituted values, and so it's just easier to kind of reason about how is the thing working. So that's all that's about. I'm trying to see. It's not whole words. Let's see. It looks like there's, oh, technically there are function factories all over the place in especially old per calls, because if you use tilde to specify like an expression, that goes through a function that generates a function out of that expression. And
Okay.
so it gets turned into a function.
I used to do that, and now I use like the / notation. So tilde was not a shorthand for function. in the same way that like the forward slash is, it was a function in itself that was creating a function factory that I was defining when I finished, like with whatever I wrote after the tilde.
It was creating a formula, which then goes through a function to turn the formula into a function.
Yeah. Okay. The same like formula used by like LM and GLM and stuff like that.
Yeah.
Okay.
And so, yeah, it was taking that formula expression and turning it into a function or a mapper. It's as mapper is the unexported function. It's thing to map with.
So it's just exploiting the special treatment that formulas have in R, in the sense that this is just some sort of an unabbreviated expression.
Yes.
Because that's the easiest unabbreviated expression to pass around the formulas.
Yeah, exactly. And so, yeah, you can do all kinds of crazy things with formulas. But it's not clear what you're trying to do. I think that's why they don't encourage it anymore. It's that same thing that they said in the chapter last week of it's vague, so you can't tell what it means. Yeah, go ahead. Sorry.
No. Yeah, you're right. I was just about to ask you that. But my question is, like, all the packages, like say Formavers packages or the Admiral packages, which has user functions, or inside their factories here, that's what it is. Like, like it's a sugar coated. Those functions are for the sugar coating for others, but inside they have factories for themselves, right?
I guess library is kind of a function factory because it's returning a whole bunch of functions. Yeah, it's returning an environment that has functions in it. So kind of, but not quite the same thing of an individual function that you call and it returns an individual function.
Because when I went into the Git location, they said one function calling other function and that function calling other function. So the exporter factory or exporter package.
But in the end, they return a thing that isn't a function. So for the most, I think most cases are not function factories. What's this? Oh, glue. Apparently, glue has some function factories.
Function factories is R-based thing, like.
Sorry, are what?
I'm thinking. The question is that function factories are like from base R.
Yeah. Like I did a quick conversation with a chat bot that okay, lots of languages have first class functions, and anything that has first class functions has the concept of function factories kind of baked in. And so JavaScript has function factories. I guess Python decorators are a type of function factories, which actually is more like what we're going to see next week, I think, the operators. So yeah, it is like it's emergent from base R. I don't know that it was something that was designed per se to be included in base R, but it happens because of the way that base R is designed.
That makes sense.
So
just real quick, the like hitter 2 or R, probably even RVest, all of those the authentication systems are generating functions to perform the authentication. So and probably other things in there. But yeah, if you dig into the hitter 2 code, there's lots of stuff where it's like generating functions to do things. So you're actually attaching a function to your call, and then when you actually make the call, it calls that function.
So it really seems to me like function factories are something that are most useful for when you're like developing convenience functions for use by like the audience or your users. If you're just like doing an analysis, don't really need to like abstract or future proof any of your functionality. You just like you probably wouldn't use a function factory.
I could see it for cases where like you do the same thing a lot.
Yeah.
Or do almost the same thing a lot. That's if you do the same thing a lot, just make a function. But if you do
Yeah.
almost the same thing, but again, yeah, I don't know. If each time, I mean, like I said, every time that we use per, which presumably, like I use per a lot,
Mhm.
and that can't, in some ways of calling that is a function factory.
Yep.
It's things like that, I think. But I can't think of specific examples. I know that I have a couple that I've done recently, but I couldn't tell you why. I remember having to go, oop, need to force that. So it's mostly in like shiny modules.
Okay.
Yeah. Right. And speaking of, I need to go work on those shiny modules. So
Yeah.
next week, I think we have people for pretty much every week, but
Should I hit end now, John, or stop or whatever the keyword is, or do we do that?
yeah,
Like
let's go. We can go ahead.